All right, so last Thursday when I was gone, I had you guys watch the lecture video from last year. Let's quickly breeze through this really quick. There was one major mistake that somebody pointed out to me, and I'll show you guys that in a second. But we talked about amino acids, and amino acids are the building blocks to making proteins, and peptide bonds are really just amide bonds, right? So they're the amide bonds connecting individual amino acids to one another. I gave you guys this guide. You don't have to memorize them. However, it's a really good guide if you go on to take biochem. It's laid out very cleanly. And then the other thing that I goofed on in the video was those NH2s on the video were OHs because I wasn't thinking clearly. And so these are all L amino acids simply because those amino groups are on the left-hand side. And then I showed you guys the acid-base chemistry for these. It's important to remember that you've got a basic site and an acidic site, so you have to deal with various pKa values. If you go through your textbook, you can see a whole list of these, but it's important to remember amino acids exist, and there's Witten ionic form at certain pHs and oftentimes a wide range of pHs. I briefly showed you guys, too, the amino acid synthesis. I got to be perfectly honest with you, these are all super old school. You won't really see them in an actual research lab. Amino acids can be bought and made so much more cheaply than they can be synthesized. But it's good to see because you may see some of these reactions on the ACS exam. The last one was an important one, and I think the video cut out a little bit early, but it was basically looking at an enantioselective reduction. So if we look at the double bond in our starting material, we're reducing that to a single bond, and then we're popping off that acyl group. And so to do an enantioselective reduction, we have to use a chiral catalyst. And there's a whole variety of chiral catalysts that are used. However, these BiNAP catalysts are pretty popular. It's the one I've got shown in that bottom corner. I don't expect you to know the mechanism for it. Just know that a chiral catalyst will only deliver hydrogen to a certain face of that alkene. All right, so let's switch gears to making peptides and not just basic amino acids. All right, there's a couple of problems when making peptides. So let's make a list of these. Problem number one is, let's say I've got one amino acid, I'll draw this in black, and we want to couple it to another amino acid, and I'll draw this in red. And we want to form a new peptide bond between that nitrogen and carbon. Will this work? Your body can do it. But if you just throw these in a reaction flask and you shake them up, what will happen? Something will happen, but not what we want to happen, right? We've got a carboxylic acid, we've got an amine. We're just going to move a proton. So the problem we have is this will just result in a proton transfer. No peptide bond will form. So you're kind of stuck in this regard. Our body is really good at making these peptide bonds, but if we want to do this synthetically, we have to be a little bit clever. And the main thing we must do is we must turn our OH, specifically this OH, into a better leaving group in order to have this reaction occur. What's one way of doing that? Tosylation is useful for alcohols. This isn't quite a normal alcohol. It's a carboxylic acid OH. We saw this in the carboxylic acid chapter, though. SOCl2, right? So we could use SOCl2. That will change that OH into a chlorine, and then we can do an amide coupling reaction. That's one way of doing it. It's pretty old school, not common anymore. Another method is to use a peptide coupling reagent. There's a whole list of peptide coupling reagents that are commercially available that are designed specifically for the sole purpose of making nitrogen-carbon bonds that are peptide bonds. One problem is using thionyl chloride is really hard to handle. It's not something you want to do in most biochemistry labs. So peptide coupling reagents are a much nicer way around this. So let's take a look at an example of a peptide coupling reagent. This is called dicyclohexyl carbodiimide. It's a mouthful, so most people just call this DCC. And it's commonly used for making new peptide bonds. There's a lot of carbodiimides that are used for this. This is just one classic example. Let's take a look at the mechanism for how this helps facilitate formation of a new peptide bond. All right. So we've got our carboxylic acid. We know we need to change that OH into a better leaving group. I'm not going to draw the full cyclohexyl rings. I'm just going to write CY. First thing that happens is a simple proton transfer where these nitrogens can act as a base and grab a proton off of your carboxylic acid. Now this nitrogen's got a positive charge on it, and we've got an oxygen with a negative charge. That means that this carbon right here is a really good electrophile because it's adjacent to the nitrogen with a positive charge. So this oxygen will actually attack this carbon and kick up electrons onto that nitrogen. Excuse me. So now we've got this group here, got an NH, and we've got a CY. All right. Now, if we look at this, this is actually a fairly good leaving group. This whole functional group over here is what's going to be converted into our good leaving group. But before that can happen, we need to have our amine attack in. So I'm going to write my amine above the arrow. This amine will attack into the carbonyl, kick up electrons. Got our amine that was added in, and then we've got the rest of our DCC hanging off here. All right, next thing we're going to do is we're going to move this proton from the protonated amine right here over to the other nitrogen. So we're just going to do a basic proton transfer. So I'm going to write plus and minus H plus. Okay, so we've just moved that proton highlighted in yellow from the nitrogen over to the other nitrogen. Now we can kick off our excellent leaving group. If we kick this down, we can then take these electrons over and move these electrons up to the nitrogen with a positive charge. So it looks complicated. However, we're reforming a new carbonyl. And this was our leaving group. This reaction is really nice because you're forming a urea, and this urea can be removed using a just plain simple extraction using a separatory funnel. So instead of having to do a complicated purification procedure, you basically mix these, heat them up, do an extraction, and you've got a new peptide bond. It's very simple, very clean, and there's a wide variety of peptide coupling reagents that you can use to make this bond. And this avoids having to deal with SOCl2 or any sort of poisonous gas. So you'll see this if you ever work in a biochemistry lab or if you do peptide coupling chemistry in an organic lab. So that's the solution to one problem. However, there's another problem. All right, problem 2 is, let's say I've got this peptide. I'm just going to abbreviate R groups. Oops, sorry. So I've got this R group coming off that alpha position, and I want to mix this together with another peptide. Or sorry, amino acid. I keep on saying peptides. Let's say we throw these together and we have DCC. What do you think a problem could be? I heard somebody say something in the back. The what? Yeah, that's a good question. So if we think about it, we've got this nitrogen. This nitrogen could attack this carbonyl. Or if we think about it, this nitrogen could attack this carbonyl. Or this nitrogen could attack another equivalent of itself. You end up with this horrendous mixture of products. So let's take a look at a couple of them. You could end up with something that looks like this. This would be our ideal situation. So we formed a new peptide bond in between there. However, we could end up with reactions where we don't get the peptide bond that we want. We actually couple individual reagents together. Sorry, this should be a single prime. And you could get two more of these, right? So you could have black and blue, blue and blue, or the inverse blue and black version of these. It's kind of like that crossed aldol reaction that we saw, where it gets pretty problematic if you just mix these together. So we've got to be a little bit creative, right? What's one strategy we could do? What do you guys think? Protecting groups, right? So if we don't want one of the alcohols to react, we could protect them. We saw protecting groups for alcohols where we use TMS. We can't use TMS for carboxylic acids. We actually have to be a little bit more creative. And then we have to use a completely new class of protecting groups for those amino groups coming off of our amino acids. So let's make a little note here that need to protect if you don't want to react. All right, so let's take a look at some protecting groups for amines, and then we'll look at protecting groups for carboxylic acids. All right. The main protecting group that you guys have actually seen for amines is called BOC. BOC stands for tert butyl oxycarbonyl. I remember when I first saw this, I was like, how are they getting BOC from this? Well, it's the butyl, oxy, and the carbonyl. I don't know why BOC got chosen over like T-BOC or something like that, but it's just the name that stuck. And it's called a carbamate. Protecting group. So let's take a look at an example of BOC being used to protect an amino group. The way we install a BOC is by using a reagent like this. This is referred to as BOC anhydride. Or if you want to go into the full IUPAC naming, it's diterbutyl dicarbonate. And you can imagine this is going to react like a normal anhydride. And you'll be able to install this whole portion, which is really just a BOC group over here. So let's take a look at the product that we'll get out. Oops. Sorry. So you can see now you've got this BOC group installed off that nitrogen, and now it's no longer an amine, it's actually a new amide bond that's really quite rugged and unreactive. This is an excellent way of protecting amines so that they don't do any sort of nucleophilic chemistry or acid-base chemistry. TFA is trifluoroacetic acid, and it's used to remove BOC groups. TBAF is used to remove silyl protecting groups. So TFA is really commonly used, and it will pop off a BOC group. Sorry about that. All right, so now that we've protected one of the amines, we have to protect the other carboxylic acids that we don't want to react. So let's take a look at carboxylic acid protecting groups. All right, so we've got our amino acid. One super simple way is to react it with benzyl alcohol and catalytic acid. What will this do? You guys know this chemistry. Carboxylic acid, alcohol, catalytic acid, Fischer, esterification. We're going to make a new ester bond. So the benzyl alcohol will install where the carboxylic acid OH used to be. We've formed our new ester using that same chemistry we've seen. This will block that carboxylic acid from acting as a nucleophile. And then if we want to remove this, we've got a whole variety of options. The Klein textbook lists quite a few, so I'll show you all of them. First one is using hydrogen gas in a palladium or platinum catalyst. That will pop it off. We're not even going to get into the mechanism of that. The next one is HBr and acetic acid. That works pretty nicely as well. Or you can do sodium hydroxide and water. So this is a really versatile protecting group, and it's really easy to remove it when you want to. However, it won't fall off under normal peptide coupling conditions. All right, so let's take a look at this. Protecting groups are used for short or simple peptide synthesis. Why do you think this strategy is not used if we were making a peptide that's, let's say, 40 peptides long? Yeah, exactly. It's a lot of back and forth. You have to put a protecting group on, do your peptide coupling, then take your protecting group off, do another peptide coupling, put more protecting groups on, do a peptide coupling. It's a huge pain.
Thanks for that question on sapling, by the way.
You what?
Thanks for that question on sapling, by the way. There's one on sapling where you have to do it back and forth.
Yeah, well, sorry. Basically, it requires three steps for each coupling. It's kind of a pain, which brings me to problem 3. Problem 3 is if it requires 3 steps for each coupling, this takes forever. So time is a problem. You don't want to spend 30 years making a peptide. Second thing is cost. If you propose this in a lab trying to make a peptide that's 40 or more amino acids long, your boss will laugh at you because you'll waste your time and cost the company a lot of money. The third reason is greenness. You're going to make a huge amount of waste. If you go through and do the atom economy for each of those protections and deprotections, you're really wasting a lot of atoms. So it's a terrible situation. So I've got a problem or a perspective idea for you guys. To put this into perspective, there's a drug called Fusion. And I think Fusion is something like over 30 amino acids long. It's a big polypeptide that's synthetically made, and it's a HIV fusion inhibitor. It's one of the last resort HIV drugs, so if you have HIV that's resistant to all of the standard HIV drugs, they give you this. It will lower your HIV levels to an undetectable amount, and it looks like you're basically HIV free. It's one of the best drugs on the market. However, it would require 114 reactions. Let's say we're a good chemist and we get 95% yields for all of these 114 reactions. Does anybody know what our net percent yield would be? If we got 95% yield for 114 sequential reactions, our net yield would be 0.3%. Fusion has a half-life in your body of 8 hours. It requires a lot of it to be injected into you because your liver very quickly wants to get it out of your body. It's a foreign peptide. So if you're getting 0.3% yield, that's a really tough situation. Fusion is very expensive because of this. It's not a simple drug to make. However, we don't make it synthetically by doing protecting groups on and off all the time. The solution that's commonly used is to use an automated system. So solution number 1 is to use solid phase peptide synthesis, which is automated. Basically, you can buy this expensive machine. You can type in the amino acid sequence you want. It's got a bunch of bottles on top with the amino acids already protected up there, and you can cross-couple them together at will, and you sit back and let the machine chug away, right? That's an easy solution. Solution 2 is even better. Solution 2 is, why should we be the ones doing it? Let's engineer some bacteria to do it for us. And this is called directed evolution. And with directed evolution, we actually have the capacity to insert genes into bacteria or yeast, and we can say, all right, I want you to make this sequence of peptides, and the yeast will just say, okay, I have no idea why you want this, but I'm doing it. And it will spit it out. So insert gene sequence into E. coli or yeast. And then you have this big fermenter you can go through. You can process the yeast or E. coli when you're done and isolate all of the drug or the polypeptide that you want out of it. This is what is far and away the most popular. There are actually research groups around the world working on this in order to make it faster, and I'm sure, how many of you guys have heard of CRISPR? Yeah, CRISPR's kind of revolutionized how quickly this is growing. It used to be a really tedious process where it would take a lot of work. You'd have to get a plasmid and get it to insert correctly, and half the time things wouldn't work the way you wanted to. With CRISPR, you can now buy a kit that's about like $30 and do it on your own in an amateur lab. So they're doing it in plants, they're doing it in yeast, they're doing it in E. coli. There's a lot of ethical debates about whether or not we should be using this, and as cheap as it is, it's becoming somewhat of a problem because people aren't stopping, they're not slowing down, they're not thinking about the ethical repercussions. So for example, there was a paper last year where a group genetically engineered yeast to make heroin. So instead of making beer at home, you could have a nice carboy full of heroin. You know, that's a great idea to have floating around the streets. So it's a really unique, cool idea. There's a huge amount of potential. There's a lot of people out there that say that organic chemistry is going to slowly die off because everything will be done by E. coli or plants, and that basically bioengineers will rule the world. There's a lot of debate about that. There's a lot of synthetic chemists that say, you know, it's kind of putting the cart in front of the horse. That may be what occurs in the next 300 years, but for the next foreseeable future, chemists will still be an integral part of that process. So let's take a look at solid phase peptide synthesis really quickly. I'm not going to test you guys on this because it's kind of complicated, but if you ever work in a biochem lab, you may see this, especially for short, simple syntheses. Essentially what you have is this polystyrene resin, and you can see this polystyrene resin right here. It's just embedded in these long cylinders, and you've got these alkylated portions coming off the polystyrene, right? So that chlorine group's coming off. If you think about this, right, you've got a good nucleophile here. This nucleophile can come, attack that carbon, kick off your chlorine, and essentially you've made a new ester, right? So you've got a new ester linkage, you've got your protected amino acid with this Bach group down here, and you're set to go for your next step. The next step is to remove that Bach group, right? So the question is, how can we remove this Bach group from those guys? TFA. So trifluoroacetic acid, those Bach groups are now gone, you've got a free amine. Then the next part of this automated scheme is to throw in another Bach-protected amino acid and a coupling reagent. Now what you've done is you've got this OH group, you've got this NH2 group, you can form your new peptide bond, which is right here. So you can highlight them right here and here. And then you've got a Bach group that's on there. The same thing can occur. You can do TFA. Step 2 would be, let me clean this up. Would be to have another Bach protected amino acid and DCC, and do this over and over and over again. And that's essentially how solid phase peptide synthesis works. And then one of the last steps is just to cleave that ester linkage by doing a simple hydrolysis reaction, and it will pop off your polypeptide. Yep.
What about this is better?
Then doing it by hand?
Yeah.
So doing it by...
A robot is doing it.
Yeah, the biggest thing is a robot's doing it, and because a robot's doing it, you can really precisely control everything. Inherently, as soon as you bring a human into the equation, you're going to spill things, you're going to drop things. It takes time. So anytime you can get an automated system, that's going to be leaps and bounds better than any human being. It's expensive though, so typically you'll only see these in biochemistry labs that do have a significant amount of funding. They also have these now for DNA. So you can work in a biochemistry lab and they've got automated DNA synthesizers. So you've got each of your amino acids on the top and it will just link it together. You go onto a computer program and you say, I want this sequence, and it spits it out. So things are getting incredibly automated right now. It's another part of the reason why I kind of breeze through this portion of the Klein textbook, is it's not really that relevant to most organic chemists because so much of it's automated now.
Is that how they make like the plasmids?
That's usually done a little bit differently. So making plasmids is more involved than just typing it into a computer program. But that's a good question. All right, so you'll be happy to know you guys made it through organic chemistry. What I've done is I've put a summary of reactions up. Like I said, these reactions are somewhat dated. We've already seen this Hell-Volhard-Zelinsky reaction. The only variant is we're going to throw in ammonia and do an SN2 to install that amino group. We've seen reactions like this with our diethyl malonate synthesis. Only difference with this is we're using a modified version, so this is exactly like the alpha carbon chemistry. The Strecker synthesis is where we form our cyanohydrin. That's really similar to just cyanide attacking into an aldehyde. Only difference with this is we're attacking it into an imine first rather than a normal aldehyde. And then we can hydrolyze our nitrile to a carboxylic acid. And then, like I said, with an antioselective synthesis, just remember chiral catalysts can be used to exclusively get one enantiomer out. Peptide synthesis is a strategy game where you have these two sticky ends. You want to couple them together using a peptide coupling reagent like DCC. However, in order to do this, you have to use protecting groups in an efficient manner. And to be perfectly honest, a lot of these are automated. So what I think we're going to do is stop it right here. I would really encourage you guys to print off the practice exam on the website. Try to take it cold without notes, and then go back and look at where your holes were and try to identify stuff like that.